Hi everybody, today we're going to price forwards and futures using the binomial stock model. Forward and futures using binomial stock. So we've already priced forwards but not futures, but now we're going to use the binomial stock model in hopes that it gives us a more interesting result. So here, as we all know, we have a stock. It goes up or down and it keeps going up or down until maturity date big T. The price of a derivative on this stock is equal to, so this is 0, so cash flow times 0 is equal to 1 over R to the T, with the expectation of the risk neutral probability at time 0 of the payout CT, where CT is a random variable for each of the different states. So each of these are different states that we might end up in, and they each have a different payout, and we weigh those payouts according to the risk neutral probability here at Q. So in the case of a forward contract, the payout CT in this case is equal to ST minus F0, where F0 is the price for the forward price we've decided at time 0. Okay, and again, it costs 0 to enter into a forward contract, which is why we end up with this sort of equation. Station Q0 ST minus F0, which implies, we can remove this term here, which implies that F0 is expected value Q of ST. Okay, so now in the case of futures, we get a payout every single period, so we can't quite make this sort of derivation. So the best that we can do, again, it also costs 0 to enter into a futures contract, but now we're only going to be able to move one step into the future. So we have this, then here it will be the payout that we get, right, is equal to ft plus 1 minus ft. Okay, and then and this should be a time t, assuming that we are at time little t. Okay, so now ft is a random variable at time t, so we can take it out of the expectation, right? And we end up with ft is the expected value according to risk neutral probability at time not 0 t of ft plus 1, which implies that ft is a martingale, and we're going to use that to no use whatsoever right now. Okay, then there was a section on dividends, so pricing options with dividends, and it's not more complicated. It's just that when you're solving the equation to find out how much stock you should hold and how much so this is solving for the risk neutral probabilities. The equation usually is this, right? Cu, and then we have ds, so x plus ry is tt. But now in the case of dividends, we also get a payout here plus c times s0 that depends on the stock price, plus c times s0, and this changes the risk neutral probability slightly. So now there's like an extra c term or something. Okay. Then there was also a section on pricing options instead of on stocks, options on a forward or a future on a stock. And the way that works is, well, you have the underlying stock, and then you have the you price the forward and the future on top of that based on these equations that we derived, right? And on top of that, we have the option, right? So it's not too much more complicated. I think I just explained it. So pricing sort of option on underlying, and there are times in real life when you would want to do this. Well, for example, what if the underlying stock is actually 200 or 500 stocks, like the S&P 500? Then you might want to price, like the future is a sort of standardized product, maybe you can instead create an option on the future instead of an option on 500 or 225 underlying stocks on futures forwards. Okay. Finally, there was also a section on what's it called again? Black-Scholes, which is, I guess, one of the first more complicated formulas for pricing options, and this is now in continuous time, which is nice. So in Black-Scholes, the underlying stock is assumed to be a geometric Brownian motion, which we covered. It's a Brownian motion, except kind of e to the power of a Brownian motion, realistically. So I don't remember the exact formula, but it was like the underlying stock is, it was like mu minus sigma squared t plus, and there was a Brownian motion here, term here, yeah, standard Brownian motion, something like this. So you can view geometric Brownian motion as the infinite, so you can see it as the binomial model with n going to infinity. That is one way to view geometric Brownian motion, and it might give you a formula for the Black-Scholes. The other way was to solve the differential equation. So as we know, in the case of Brownian motion, the underlying stock is changing according to this differential equation, mu, which is the drift, st dt plus sigma st dwt. I think that's correct. And so then we have an option price C that depends not only on the time, but also on the underlying stock. And the stock follows this differential equation, so it's sort of more confusing. So then according to Ito's lemma, there is sort of a nice way to write the differential equation for dc of t, and it has like two terms here. And so we use that, and at the same time we create this nice random variable xt, which is equal to, so this is where we're going to replicate the option payout using, this should be xt plus sort of bt yt. So here is our the price of the option, and we're going to try to replicate this ct using this pt, and then we can show that they're the same, and then we can derive a differential equation for this, and we end up with a formula of C, which is the Black-Scholes formula, which is there's a big term here, and then another big term here, and it's sort of complicated, and there's like normal distribution stuff here. So yeah, I think that's it. This is the final lecture for this course. So see you next time.